Kia ora koutou everyone. So as Stephen introduced, I'm Neryda, and I'm going to further introduce the versatility of the Mars scanner by looking at scanning geological samples with Mars spectral CT. So we're going to answer these four main questions today. Basically, why is Mars CT useful for geology? Can the Mars system be optimized for scanning rocks? Can we successfully visualize rock samples and provide superior information to geologists? So for centuries, we've studied geological features and landforms to improve our understanding of Earth processes. But it's the rocks and sediments that make up these geological features that have become increasingly important to help us gain a deeper understanding of Earth systems. So I was provided with a number of rock samples from the UC Geology department. The first of this is the Plutonic Igneous rock, and so these are formed deep within the Earth's surface by the slow cooling of magma. And so we are interested in the crystal phases, specifically the plagioclase crystal, the orientation and alignment of this crystal to give us an idea of the processes that this rock's gone through to get to its final stage. The next is a volcanic extrusive igneous. So these form on the Earth's surface by the cooling of lava. And so when this lava cools, bubbles form in the lava and they freeze, and so this leads to pores. So we're interested in the pore size and connectivity, or porosity and permeability, and this gives us information on fluid flow through these pore networks at different reference sites. And so the first sample is Ignimbrite from the Topor volcanic zone, and some other samples from a caldera in Iceland. The last sample was Andesitic Tuff, which we're interested in the fault plane geometry and seeing if we can see that in 3D. So currently geologists use a mixture of scanning electron microscopy and electron backscatter diffraction, and this involves taking 2D images of a rock sample and slicing away to get more information. Up in the top right we've got a petrographic image of plutonic igneous and the electron backscatter data. And so this is found by shining an electron beam on this 2D slice, and the crystal planes will reflect and give us this orientation map. And I don't know about you, but I don't really understand what's going on in the orientation map. Then we've got the helium pygnometer, and so this pumps a known gas of helium into a rock sample to provide us with the connected porosity. But this doesn't take into account the isolated pores, and so without grinding down the sample into a powder to find the solid density, we wouldn't get an accurate measurement of the total porosity. So Mars spectral CT, with its photon counting ability, can provide good differentiation between the materials in the rocks. It can give us a good spatial resolution, and it can provide the 3D reality. So geologists struggle with trying to visualize, use their 2D data to imagine the 3D. So Mars can do all of this and keep our lovely rock samples intact. So we were provided with all of the composition data for each of the rocks, and from here the linear attenuation curves were plotted for each of the materials present in a sample. We then used the energy bins, indicated by the vertical lines, to optimize the difference in materials for the materials within the sample. The filter, voltage, current, and exposure time were all features of the protocols that we altered to try and optimize the protocol for rocks to reduce common image artifacts such as blurring or beam hardening. This protocol showed that it was optimized for rocks, and so the following results show all of the samples that we managed to visualize. So the first is the Plutonic Igneous, and in the top left we've got the 3D rendered view plus the axial, coronal and sagittal cross sections of the rock, and from here we were able to get a video of this rock sample. We were able to see the shape and form of the crystals within this rock sample. Next, we scanned this with a pure plagioclase crystal, so we were able to utilize the Mars Vision thresholding to just see the crystal of interest, shown here in the yellow. The next is the Ignimbrite, and so the image on the top is a scanning electron microscope image in 2D, and below is we're slicing through the axial views of a Mars image, and you can see that these pores and the image quality are definitely comparable. The last Ignimbrite was the Iceland samples, and the top image is a scanning electron microscope image of scale 100 microns, and then below are the Mars images of 50 micron voxel size. So we can see the internal structures of the rock as well as the individual crystals really well. We do need to do a bit more work to try and determine the actual features inside each voxel size and see if we can compare them exactly to what the geologists have slice by slice. And the last sample is the Andesitic Tuff, which this is really cool. So we can see the fault planes in the blue and then in the thresholded image. So this is really good to be able to visualize the geometry of these, and they can get a better idea of how fluid would flow through these fractures. So we can visualize them, but so what? What is the sort of analysis that we can do to provide to geologists? So a very basic set of thresholding was provided to try and segment the rock between pores and rock sample. So intensity threshold was set in MATLAB, set to rock and pores. So these videos down here are just the pores. So we can see we're able to visualize the pores, but can we quantify this? So another very basic function determines all of the connected elements within these threshold pores, and from here we'll split this into connected porosity and isolated porosity. So from here we were able to take the data that was given from geologists of the connected porosity found from the helium pycnometer and compare it exactly. And so what we'd do is we'd get the connected porosity, compare it, and then from there we'd be able to find out how much of the rock was isolated that hasn't been picked up, and what's then is the total porosity. If it didn't match, we'd then reiterate, set another threshold until we managed to get it within a percentage. So the first result is with the Iceland Ignimbrite, and so on the left is all of the pores that came out as connected, and on the right are all the pores that came out as isolated. The connected porosity value was within about 1.8% of the actual measured connected porosity, which was really good, and fell within the uncertainties of the connected porosity. And just sort of a percentage shows that the isolated porosity percentage with the total porosity is about 2.1%. This rock sample was really interesting in that when the thresholds were set and the measured connected porosity and the one we received from the Mars data was within 2.1%, the isolated porosity actually was about 67.2% of the total rock. So if they were just using the measured connected porosity from geologists, they would be missing a whole lot of porosity information. So the next step is to explore the variability in the data and provide uncertainty measurements for all of the results. Setting the regions of interest, if you scan the rock sample sort of on a tilt and try to take region of interest through the rock and you get air, you sort of reduce the amount of region of interest you can have. And setting the attenuation thresholds is really important to make sure that what you're actually looking at is pore and is rock. And so that comes down to your voxel size and what elements are within each voxel, because it will just take the average intensity. The next is using the Mars Microlab to scan all the remainder of the rock samples to get a bigger sample size for data. And then utilising this connectivity code to investigate the plagioclase crystals and the orientation. And then automating the connectivity porosity code. So in conclusion, Mars CT is successful in optimizing protocols for visualizing samples, and the preliminary analysis shows that we do have the ability to provide data for geologists that would be useful. Thanks. Any questions?